Hello everyone, in this part of the lecture we are going to study the effect of zeros on the step response of the systems. To start, let's have a look at these two transfer functions. The first one is g1, which has two poles at -1 and -2. So there are two poles at -1 and -2, and there are no zeros. In the second case, we have g2, which has the poles at the same locations at -1 and -2, but it also has a zero which is pretty close to one of the poles. So it's at -1.1. Then if we expand these two transfer functions, we will get them in this form. So g1 will be equal to 2 over s plus 1 minus 2 over s plus 2. And then for g2 we will have 0.18 over s plus 1 minus 1.64 over s plus 2. And you can see that the coefficient that we have in the numerator of the part with the pole at -1 for g2 is decreased significantly. So initially it was 2, now it is 0.18, less than 10% of the original value. And that's because we have a zero which is nearby that pole. So when a zero is placed near a pole, that zero will significantly decrease the effect of that pole in terms of the response of the system. If we place the zero and the pole at the same location, then the zero will cancel the effect of the pole completely. Just keep in mind that this happens for the stable poles, okay? So since we had zero close to the pole at -1, the corresponding coefficient is drastically reduced. If you had put it exactly at -1, then the effect of that pole would be completely cancelled and the coefficient would be equal to 0 indeed. Let me show you maybe in the pole zero map. So initially we had this two poles at -1 and -2. Then by placing a zero near -1, this zero which is close to the pole at -1.1 drastically reduces its coefficient in the response of the system. So that just gives you an idea of what happens to the response of the system when we add a zero to it. But let's see what happens to the step response of a first order system when we have an additional zero. When we have a zero, we can write the transfer function for the first order system in this form: 1 plus s times alpha t over 1 plus s times t. This means that we have a pole at -1 over t and a zero at -1 over alpha t. If you consider the variations in terms of the alpha, so location of the pole will be fixed. We'll have it at -1 over t, but the location of the zero will vary. It might be here or anywhere, depending on the value of the alpha. And we can see that as alpha increases, when alpha increases, it goes towards, let's say, big positive values. The zero moves towards the origin. When alpha decreases, the zero moves further from the origin or towards -infinity. Maybe I can write it over here. If alpha becomes too small, then zero moves towards -infinity. Yeah, and vice versa. If alpha becomes too big, then zero moves towards the origin. And this is for positive values of alpha. Okay, so for now we assume that the additional 0 is on the left half plane. Then for the step response of the system, you can see that the initial value for the response c at 0 plus will be equal to alpha. So this alpha will determine from where the step response begins. Keep in mind that without a 0, without an additional 0, I will draw it here, without an additional 0, the step response of a first order system starts from 0. Okay, and it will be somehow similar to this graph that I just drew in green. So it was 0, and then without a 0, only a single pole, it moves like this. Then in this example, you can see several cases. When alpha is equal to 0.5, we will have this graph. And when alpha is equal to 1.5, we will have this graph. You can see that the initial value for the response at 0 plus is equal to alpha. And since we have the DC gain of this system equal to 1, the final value will be equal to 1, and as a result, it will start the response will start to decrease, or it will start to increase. And as alpha goes towards 0, when alpha goes towards 0, the step response of the system will become similar to the case where we have no 0. So in this way, let's say that alpha moves towards 0 in this direction, if you consider the different step responses that we just have drawn. And over here, alpha is equal to 0, and afterwards, alpha will become negative. When alpha becomes negative, then the step response will start from negative values, and it will obviously increase and move towards the final value, which is equal to 1. So that's what happens to the step response of the first order systems. Now, if we consider the general case, we can have an intuitive interpretation of the effect of the zeros. We can take a transfer function such as g prime into account, and then add a 0 at minus 1 over tau to this transfer function, which will give us another transfer function which is denoted as g. So we have g prime as the initial transfer function without a 0, and then we have added a 0 at minus 1 over tau, which means that we have multiplied it with 1 plus s times tau. So the tau determines the location of the additional 0. Okay, it will be located at minus 1 over tau. But then we can also rewrite this, the new transfer function g that we get, we can rewrite it in the form of g prime plus s tau times s times g prime. Okay? And then if we look at the step response of the same system, so if as the step response give me a second. Okay, so if as the step response of the system in the time domain, we will get the step response of the new system equal to the step response of the original system plus tau times the step response of the system, which is denoted as s times g prime. And you know that it will be the time derivative of c prime. Okay, I can also write it in the Laplace domain. C of s will be equal to c prime of s plus tau s c prime of s. And then in the time domain, we will have this situation. And you can see that in order to obtain the step response of the new system, we need to take the original step response and then add the derivative of that original step response with a coefficient to the step response itself. And then we will get the step response for the new system. You can see an example which is drawn here. So the one that I'm highlighting in yellow is the step response of the original system. The one that I'm highlighting in green is the time derivative of that step response. And then if we add these to each other, we will get the step response for the new system, which is the old system with an additional 0. And you can see it all drawn over here. So as in the steady state, the time derivative of the step response becomes equal to 0. You can see that in the steady state, the system with 0 and the system without 0 have the same, let's say, response, or the final value for the step response. Something to notice here is that depending on the value of the tau and its sign, these two step responses that we have could be quite different than each other. If tau gets smaller and smaller, C and C prime will become more similar to each other. And when tau becomes smaller, when tau is smaller, it means that 0, the additional 0, is moving further from the origin. So the 0 moves towards minus infinity. But as tau becomes bigger and bigger, the 0 moves towards the origin. And it will have a bigger effect. So this is in general a good thing to remember. If the additional 0 is closer to the origin, its effect will become bigger. If the additional 0 is further from the origin, it's towards minus infinity, its effect will be smaller and smaller. You can see another example which is shown here. We have a second order system which has two poles at minus 1 plus minus j 2.828, and there is an additional 0, let's say, at minus 1 over tau. And you can see the step response for different values of tau in the graph which is shown here. So the one that I'm going to highlight in yellow is the one without the additional 0. So this one. This is the one which has no 0. And then a 0 is placed at different locations. So you can see it initially it's at minus 10, then at minus 5, at minus 3. 3 cases are shown here. And you may also notice over here that as the 0 is further from the origin, the step responses are closer to each other. And as 0 moves towards the origin, which is this case, let's say, you can see that the initial system's response is different than the system with the additional 0, as you can see here, and I just highlighted. So as 0 moves towards the origin, its effect becomes bigger and bigger. Keep in mind that for these cases, the value of tau is positive. Okay, so 0 is on the left half plane. And as a result, we can see the effect of the 0, especially in this form for the case of second order systems, that it will kind of have an anticipative effect. Because it looks like the step response of the system is shifted towards the left in the time domain graph. Yeah, you can maybe have a second look over here. So this is the original one. Then as we introduce the 0, and especially as it moves towards the origin, it looks like we are shifting the response towards the left side, and it's kind of having an anticipative behavior. And obviously the peak time decreases and overshoot increases. You can also see them here. So this is the peak time for the system without the additional 0, then peak time moves here, moves there, and at the same time you can see that the peak value also increases as the 0 moves towards the origin. Alright, but that was for what we had for the positive values of tau. Now we can see what happens when tau is negative. When tau is negative, we know that our 0 is located at -1/tau, and if tau is negative, then z will be positive. Positive z means that we will have the 0 on the right half plane somewhere over here at -1/tau. We will call our system a non-minimum phase system, so this is something to keep in mind for now. But later we will see why such a system is called non-minimum phase, especially when we talk about the phase of the system, okay? Let's see what happens. If we find out the initial value of the step response, c at 0 plus will be equal to 0 for the second order system with an additional 0, okay? So omega n squared times 1 minus s tau, or we could write 1 plus s tau, but for negative values of negative values of tau, over s squared plus zeta omega n s plus omega n squared. So for this system, we have the 0. We have a single 0 which is located at the value of tau, 1/tau. Let me write it again. 0 is located at 1/tau. So when tau is bigger than 0, tau bigger than 0 means that we will have this case. The 0 will be located on the right half plane. But in terms of the initial value of the response, c at 0 plus, we can see that it will be still equal to 0. But there will be an undershoot, because if we find out the c dot at 0 plus, or the time derivative of the response at 0 plus, it will be equal to minus omega n squared times tau. For positive values of tau, this will be a negative value. And since the time derivative at 0 plus is negative, we will have the value of the output will decrease, and then there will be something that we call as undershoot. So initially it will go down, depending on the value of the tau, it will go down, and then eventually it will come up, and the final value will be the same as the case without an additional 0. You can see different values here. For tau equal to 1, 3, and 5, basically our value for tau will be positive, so these are plus. For tau equal to 1, 3, and 5, we will have zeros located at, so 0 will be located at 1, 1/3, 1/5, and you can see that as the 0 moves towards origin, in these three cases, 0 moves towards the origin. Its effect becomes bigger and bigger. Yeah? So the amplitude that we have for the undershoot becomes bigger and bigger. If 0 moves towards infinity, plus infinity in this case, its effect will become smaller and smaller. So when we have the 0 on the right half plane, there will be an undershoot for the step response of a second order system. We will call the system as the non-minimum phase system. This is an important property that you need to keep in mind. While if the 0 is on the left half plane, there will be some anticipative behavior for the response of the system. Okay, but let's see when such a concept could happen, could be the case in practice. We can take a typical example of longitudinal dynamics control of an aircraft. You can refer to the textbook for more details regarding the model that is used to describe the behavior of the aircraft, but over here I will provide you let's say short explanation. We assume that the aircraft is flying at the constant altitude of h bar. When the elevators are turned up, elevators are here, so they are shown in black over here. When the elevators are turned up of an angle delta E, and delta E is considered positive downwards. Okay, so this will be indeed the direction in which the elevators are turned in a positive way, and now we assume that they are turned up of an angle delta E. So then the aerodynamic force will push the elevators down, because the airplane is moving in the air. There will be some aerodynamics force which will be acting on the elevators, and they will push the elevators down. And then as a consequence, the aircraft will rotate about its center of the mass. Over here we have the center of the mass for the airplane. Since the elevators are pushed down, the elevator will start to rotate. As the elevator rotates, at the first moment, and we have the altitude h will slightly decrease below the h bar. And we assume that the elevator rotates of an angle alpha, okay, which is considered positive upward. So this is the positive indeed direction for alpha. At that moment, the altitude h will slightly decrease below h, but then since the airplane is rotated by the angle alpha, there will be lift force on the wings. So the wings will be also rotated as with the angle of alpha, and then there will be forces applied on the wings because the airplane is moving forward. It is rotated by the angle of alpha, so the amount of the force which is applied on the wings will increase, and as a result, and that is proportional to the value of alpha, and as a result the altitude h will increase above h. So h initially went below h bar, and then after a while it increases above h. The pitch rate q will become proportional to delta E as well. Okay, so let's see over here the transfer functions that we have for the simplified unit transfer functions that we have for our aircraft model. We have gh, which is equal to q over delta E, and it's given in the form of 30 times s minus 6 over s squared plus 4s plus 13. And then we have gv, the next transfer function, which is h over delta E, and it's equal to 30 times s minus 6 over s times s squared plus 4s plus 13. So we have two transfer functions, one for the pitch rate and one for the altitude, considering the delta E, which is the angle coming from the elevators, as the input. Now we want to obtain rise time, overshoot, and 2% settling time for the negative unity step response of GH. So we will consider this transfer function, approximating it as a second order system without zero. And then we will see what can we say about the response of GV to a positive unit impulse. So you can see that this is a second order system. GH is a second order system with a zero. If we want to approximate it with a second order system without zeros, we will keep the denominator the same, s squared plus 4s plus 13 plus 4s plus 13. And then we will remove the zero, let's say, from the numerator, okay? So we will have 30 times minus 6. We just need to keep the DC gain of the system the same. So GH at 0, the DC gain over here will be equal to 30 times minus 6 over 13, and it is indeed the same over here. So we keep the DC gain the same, but we kind of remove the additional 0. Then we have a second order system. We can find out the required step response parameters, TR, MP, and settling time, by referring to the values that we can get for zeta and omega n. So 4 is equal to 2 zeta omega n, and 13 is equal to omega n squared. Out of this, we can find out omega n, square root of 13, and the value for zeta. Once we have those values, we can easily find out the value for TR, the rise time, which is 1.8 over omega n, the MP overshoot, which depends on the value of zeta, and the 2% settling time, which is 4 over zeta omega n. And in that case, we will have an estimation of the values for the step response parameters. What can we say about the response of GV to a positive unit impulse? So GV, we can see that it is different than the GH only by this pole at the origin. If we want to find out the impulse response of the system GV, and I can show it with CV, it will be equal to GV times 1, because the Laplace domain, let's say, equivalent to the impulse input is equal to 1. And then it will be also, if I compare it with the step response of GH, CV will be indeed equal to GH times 1 over S. And this is indeed the step response of the GH. So the impulse response of GV will be indeed the same as the step response of GH. You just need to also pay attention to the positive or negative input, yeah? In the first case that we just considered, we considered the negative unit step response. Indeed, if we draw the positive unit step, it will be, let's say, always negative. In order to keep our definitions of the rise time, settling time, and overshoot, we consider the negative unit step. In the case of negative unit step, we will have the step response in this way, and then we can refer to our definitions that we had for the rise time, settling time, and overshoot. Alright, now we will use the Matlab in order to plot the unit step response of the GH, and then we will evaluate the accuracy of the obtained approximated value. I will also provide you the exact values for TR, TS, and MP over there, because I will just plug the values that we get over here for omega n and zeta. Alright, so here we have our Matlab code. We have the GH implemented in the form of a transfer function, 30 times 1 minus 6 as the coefficients that we have for the numerator, and 1 for 13 as the coefficient that we have for the denominator. We also have the GH under APX, which is the approximate system, by removing the 0 at plus 6. So the transfer function will be in the form of minus 180, which is 30 times minus 6, and the denominator will be the same. And then we have a figure in which we draw the negative step response of of GH and the approximate system GH underline APX. Keep in mind that I have added this negative sign over here to draw the negative step response of those systems. You can see the step response of those systems drawn here. The one that is in blue is the actual system GH. You can see that we have an undershoot because there is a 0 on the right half plane. And then the rest of the response of the system, you can see that it is kind of shifted towards the right side. The final value is the same as what we get for the actual system. And the one that we see in green is the step response for the approximated system. So for the approximated system where we just removed the 0, the additional 0, we have the response for a second order system, which is in the underdamped case. I've also got the step info for those two transfer functions. So step info of GH gives us the step response parameters for that system. And with this command, I'm just displaying them over here. Over here, we see the step response parameters for the actual system. The rise time is equal to 0.4297. Settling time is 1.74. Overshoot is 13%. We have the undershoot of 12.0931. The peak value is given and the peak time is also given. Then we have the step response parameters for the approximated system. You can see the values over here for the approximated system. The rise time is equal to 0.4854, which is a bit more than what we have for the actual system. The settling time is smaller. The overshoot is a little bit bigger than what we have for the actual system, and also there are differences in terms of the peak value and the peak time. So these are what we get from the step info command for the approximated system. On the other hand, we are also referring to the formulas that we had in order to calculate the values for the rise time, settling time, and overshoot, referring to the values of omega n and zeta. We have omega n equal to square root of 13 and zeta is equal to 4 over 2 times omega n. And then for rise time, we have 1.8 over omega n. For the settling time, we have 4 over zeta omega n. And for MP, we have the relation with the zeta only, okay? So omega n is not here. And then you can see the approximated values over here. The rise time is equal to 0.4992, which is somehow close to the approximated system rather than the actual system, and that should make sense. The settling time is equal to 2 seconds. And from the approximated system using the step info, we have 1.6, and for the actual system, we have 1.74. And the overshoot is equal to 12.31, which is again closer to the overshoot that we get from the approximated system using the step info command. So keep in mind that always these are approximations that we may get for the step response parameters, but with the step info we get the actual values indeed. So these are what we get for the step response of GH and its approximated system. Now we want to also have a look at the impulse response of GV. So I have drawn both of them here. So you can see for the positive impulse response and negative impulse response. Yeah, what you see in red is the impulse response of GV for a positive impulse indeed. Yeah, that's in red, and you can see that it becomes positive and then it goes towards minus 15, and at the end it has some final value. If you get the negative impulse response of GV, it is drawn in blue, and you can compare this blue graph with what we have for the step response of the actual system in blue, and it is drawn here. So basically they will be the same. Okay, they will be the same. There will be the undershoot over here and then overshoot over here. After some oscillations, the final value will be obtained, and this final value will also be the same as what we get over here, because basically they are the same. Yeah, the negative impulse response of GV will be equal to the negative step response of GH. Okay. All right. So that's how we can analyze the step response of the system and how we can get the step response parameters of the system referring to the transfer function. Thank you for watching this video.